Hey, what's up YouTube? In this video, I'll be showcasing an implementation of the dual depth foliage interaction technique demonstrated in the God of War Tech Talk at GDC 2019 using blueprints and Niagara. To this day, this Tech Talk remains one of my favorites. It covered a lot of topics I'm passionate about, and the solutions presented were absolutely fantastic. But then again, Santa Monica rarely disappoints. And Sean Feely did an amazing job with the presentation, all while sipping on his milk carton like a boss. Legend. Anyway, my implementation of the dual depth technique is just that, my own interpretation. It does not perform quite as well as I'd like because I kept it entirely in blueprints, and sadly we'll have to jump through a few hoops to make it work. But on principles, it's a very sound technique, and convert it to C++ and you'll have a really solid solution for creating cheap yet believable interactive foliage. It's mostly tailored for small plants and grass though. It also has a few quirks, but more on that in a minute. Now, it's a pretty advanced system, so I assume you have a good grasp of blueprints and Niagara to start with. I have a habit of moving through things quickly, so I apologize in advance if anything's unclear. Feel free to leave questions in the comments below. Alright, let's dive in. So, what is this dual depth technique? In a nutshell, the idea is to rasterize the depth of objects from underneath. With that, you can determine the Z location of surfaces, compare it to some arbitrary value, like the height of your foliage above the ground, and use that to render the interaction depth. That depth is stored in one channel. In a second channel, the depth is gradually faded over time. The difference in height combined with the fade rate gives you the time of the last interaction. And both channels are overwritten when a new interaction depth is greater than the faded depth. This creates a sort of depth history, which allows you to derive the time of the interaction, but also the quote-unquote intensity and direction of the interaction using derivatives. To calculate the direction, sample the held depth at the current position, as well as to the left and above. Compare the samples, and that gives you the slope of the depth. This works because surfaces are approximated using spheres and capsules. Once rasterized into the depth channel, the depth values typically vary somewhat smoothly, enabling you to calculate the slope. With this information, you get a 2D direction, and the amount of slope can be used to determine the amount of interaction. Where the slope is near zero, that's the center point of the sphere or capsule, and that's where the foliage should move the most. Where the slope is the greatest, foliage should move less. Now, if the depth is nearly identical across neighboring samples, resulting in zero derivatives, you can always fall back to a default direction. Coupled with a spring-like animation using a cosine and exponential term based on the time of the last interaction, you can apply a cheap world position offset to the vertices. Combine this with the spherical reprojection technique, also described in the same Tech Talk, and which I've also covered in previous videos, and you get a fake rotation with very little cost and effort. The great thing about this technique is that it handles the information very effectively. You can jump over grass and it won't be affected by it. It may sound trivial and obvious, but in reality, most other techniques used to achieve similar effects often struggle with the Z-axis. That's the theory. So the first order of business is to approximate static and skeletal meshes with simple mathematical shapes, spheres, capsules, and boxes. Now, we could render the depth of static and skeletal meshes directly using something like a scene capture component, which I've demonstrated in other videos. However, this approach is usually frowned upon because on paper, it's not the most efficient way of doing things. A scene capture component can be costly, and rendering skeletal meshes multiple times is generally not recommended, even if it's just to rasterize the depth, especially considering that for such effects, you usually don't need the actual precise surface depth. so more often than not, surfaces are approximated using simple shapes. And this can actually be beneficial because rendering surfaces may introduce small, high-frequency details that don't always work well with algorithms like this one. Approximating with larger and smoother shapes can sometimes work in your favor. Now, for today's video, I'll keep it relatively simple and use a brute force approach, which shouldn't be an issue unless you want to scale this system massively. Actually, I'll be using a technique I've demonstrated before and explained in a previous video. I'm going to attach shapes to the bones of skeletal meshes and shapes to the sockets of static meshes. Then, every frame, I'll fetch the transforms of these shapes and construct a buffer to send to the GPU. Next, on the GPU, using a render target, I'll ray trace these shapes for each pixel to get the Z location of their underlying surfaces and render the overall minimum Z value. Now, if you're familiar with Niagara and its rigid mesh collision interface, that's essentially what it does. This interface can fetch collision data for both skeletal and static meshes, meaning their rigid bodies. It supports capsules, spheres, and boxes. And on tick, it does the fetching and posing, so you end up with an interface that provides a list of posed capsules, spheres, and boxes that it can loop through to fetch the closest element, the closest distance, etc. Now, unless I'm mistaken, this is almost exactly what we need. This is what we want, but sadly, none of these functions will work for us. Here's the issue. It's all about getting the minimum distance. And getting the minimum distance isn't quite the same as rasterizing the depth from underneath. And this image should help explain why. This is what we get, and this is what we want. And as far as I know, the interface doesn't expose a way to manually iterate through the elements buffer to implement custom logic. So again, unless I missed something obvious, this interface won't do the job, and no other interface will either. So we'll have to rebuild it using blueprints, and that will be our performance bottleneck by far. However, if you manage to port it to C++, or even better, modify the engine and add the necessary ray trace function for this interface, you should be able to build a much more performant system. Note that this is still a brute force method, meaning just like this interface, we'll iterate over all shapes for every pixel. Since ray tracing against simple shapes isn't that expensive, this won't necessarily be an issue unless, again, you're pushing the system too far and trying to rasterize hundreds of shapes. At that point, you'll want to use some sort of acceleration structure, and I hope to make a video on that topic sometime soon. Fingers crossed. So let's start by describing static and skeletal meshes using basic shapes. If you were working in C++, you could probably just fetch the rigid body data directly from static and skeletal meshes, similar to how Niagara's rigid mesh collision interface works. In blueprints though, that's not an option, so you have to come up with alternative solutions. I've created a few blueprint structs to define mathematical shapes. Here's a struct for describing a sphere. It contains a float for the sphere's radius, a name for the bone or socket it will be attached to, and a vector to offset the sphere from the bone or socket's origin in local space, similar to how we can offset rigid bodies. Same concept, just without a way to visualize it, unfortunately. Next, here's a struct for defining a capsule. It includes the capsule's radius and half height, along with a rotator to control the capsule's orientation relative to the bone or socket. Again, something we can do as well when tweaking rigid bodies. Then I have a struct to define a box using a vector for its XYZ extent. That's it. Finally, I've created a struct to describe a skeletal mesh using a skeletal mesh component variable and including all the necessary shapes. These are the three blueprint structs I just went over. And I have a similar struct to describe a static mesh, using a scene component variable. These structs are used in the Dual Depth Manager blueprint, which is just a basic actor. It does a few things though, like managing the Niagara system we'll use to rasterize the shapes. But first, let's focus on the basics. This actor blueprint has two important functions, one to register a static mesh, and another to register a skeletal mesh. That's what I'm doing here in this character blueprint, right? I get the manager from the scene, and don't worry about that function for now. And here I simply send the character mesh along with a bunch of capsules and spheres attached to different bones to approximate it. Here I spawn ragdolls and do the same thing. And here I also spawn basic physics actors. I call the add static mesh function this time, but the same principle applies. I provide the correct shape to best describe the static mesh. So a sphere for a sphere, a box for a box, you get the idea. So these functions allow the manager to keep track of skeletal meshes and their attached shapes, as well as static mesh components and their attached shapes. Here I perform a safety check, and here I simply ensure that the same skeletal mesh is not added twice. The same goes for static meshes, right? Then I keep track of the amount of capsules, spheres and boxes used by both skeletal mesh components and static mesh components. I also keep track of the combined number of capsules, spheres and boxes, as well as the total number of shapes. And the reason for this is the following. We are going to mimic Niagara's rigid mesh collision interface and create a single buffer to contain all the shapes. We'll fill the buffer with all the capsules first, then the spheres, and then the boxes. And by keeping track of the number of capsules, spheres, and boxes, we can determine where each type of shape starts and ends within the buffer. Capsules are stored first, so they will occupy indices from 0 to number of capsules minus 1. Then spheres will start at the number of capsules and end at the number of capsules plus number of spheres minus 1, and so on. We'll send these indices to the GPU along with the buffer itself, which will allow us to iterate through it by shape type. That means we can iterate over all the capsules first to call the appropriate code for ray tracing capsules, then iterate over the spheres to ray trace spheres, and so on. This way we won't need to manage separate buffers and performance will likely be improved. In short, I keep track of the number of shapes for each type when adding or removing static mesh or skeletal mesh components from these arrays. Now that I have these two arrays, I can iterate through them to build the shape buffer that will be sent to the GPU. For this, I use a Niagara data channel to describe each shape's world position, extent, and orientation using a quaternion. For spheres, we only need the x component of the extent to store the radius. For capsules, the x and y components will store the radius and half height, and for boxes, the full xyz components will store the box's extent. That's all we need to send to the GPU. Well, that and the information about where each shape is stored in the linear buffer, right? Capsules come first, then spheres, and then boxes. This is where keeping track of the number of shapes come in handy. So the capsule buffer starts at 0 and ends at num capsules minus 1. The sphere buffer starts right after that and ends at num capsules plus num spheres minus 1 and so on, just like I explained earlier. These indices are sent to Niagara using a simple integer array called elements, which you can see here. All you need to do is create one like this, easy peasy. Next, I want to fill the shape buffer, and for that, I use the write to Niagara data channel batch function. I know ahead of time how many shapes this buffer will contain, thanks to keeping track of the number of shapes when adding and removing static and skeletal meshes. I don't want to iterate through them all every tick just to count shapes, right? Anyway, this next bit might look a bit complicated, but it's not as bad as it seems. Keep in mind that we need to build the array for the GPU in a deterministic way. Capsules first, then spheres, and finally boxes. So that's what I do. I start by filling the buffer with the list of capsules for both skeletal meshes and static meshes. For each capsule, I get the corresponding static mesh or skeletal mesh component, then retrieve the world transform of the bone or socket. In case of static meshes, if there's no socket, I get the world transform of the static mesh component instead. With that transform, I can construct the posed capsule. So the location of the bone or socket offset by the specified offset. And I also account for local rotation. Then I output the sanitized radius and half height. These values are packed into the three variables I mentioned earlier, position, extent, and quat, and written into the Niagara data channel, one capsule at a time. Now, in case something goes wrong, it's important to still write default values for any invalid shape. Otherwise, we'd mess up the expected number of shapes, and the indices would be wrong. So yeah, here I build capsules, and here I build spheres following the same principles, and here I build boxes. Once that's done, I have a linear buffer containing capsules first, then spheres, and then boxes. Each shape is described by a position, orientation, and the necessary extent information specific to that shape type. And to debug these shapes, it's really simple. Just call the drawDebug functions for capsules, spheres, and boxes. At this point, we have a Niagara data channel containing data that fully describes all of these shapes. So, time to rasterize them. Let's take a look at the Niagara system. The rasterization process involves a local-to-world conversion technique that I've already explained in a previous video, but I'll quickly go over it again. First, I'll rasterize the depth of shapes locally, around a specific location, in this case, the character's location. Then I'll convert it to world space. The reason for this is that this dual depth technique needs to be persistent and spatially stable. Rasterizing locally means things move relative to the character, which makes it impossible to create persistent effects. If we move around, stationary objects would appear to move relative to us, leaving a trail behind, which is not what we want. Instead, we need everything to move relative to the world origin, so static objects remain stationary and moving objects stay in motion, if that makes sense. In this Niagara emitter, I've disabled a few things that are not relevant for now, so let's focus on what's enabled. First, I create a 2D grid to store the depth using a half-float format, which should be precise enough for purposes. The 2D grid size is set using user parameter integers and a custom module. Nothing fancy. Think of a 2D grid as a render target, but more versatile and designed to be iterated on. Next, I set a 2D render target. It points to a user parameter render target texture object, which in turn points to a render target asset. I override its format to RGBA 32 bits, and its filter mode is set to nearest. Then I set up another 2D grid, this time with a 32-bit float format. Their sizes are set here using the same user parameter integers and custom modules as before. Render target here, and grid 2D there. This second 2D grid is used to store and iterate on the persistent dual depth, while the render target is used to export it for sampling in materials. Finally, I create a data channel reader and specify the Niagara data channel asset. Okay, so in this first simulation stage, which always executes and iterates on the grid 2D meant to store the rasterized depth, well, I do that. I rasterize the depth, and this is a multi-step process, so buckle up. Since this simulation stage iterates on the 2D grid, Its execution index corresponds to the linear index of the grid cell currently processed by the GPU. By knowing the number of cells in the grid, in X and Y, we can deduce the X and Y indices of the current grid cell from that linear index. This also means we can convert that to UVs by dividing by the number of grid cells in both X and Y, which is what this node does. Next, I shift the UVs by 0.5 so that 0.5, the center of the grid, becomes 0. This is because we want things to be centered on our character, which acts as the quote-unquote origin at the center of the texture. Next, we multiply the result by a value in centimeters to describe the area we want to rasterize around our character in both X and Y. For example, say it's 2000 centimeters across both axes. Since that 2D vector is a user parameter, it's customizable via the manager blueprint, allowing you to control how far the effect is visible around the character. However, a larger area size might require a higher render target and grid resolution, something to keep in mind. Nothing's ever free. Then we simply shift this by the character's location to convert the UVs into world space coordinates. And we get the character's location this way because in the manager blueprint, on each tick, I snap the Niagara component's world location to the character's mesh world location. There's a bit more to it, but I'll come back to that in a second. The gist of it is that this Niagara component is located at the feet of the character. So this position corresponds to the character's feet. So if the character is, say, at this coordinate in world space, the center point in the grid, initially at UV 0.5, gets shifted by 0.5 to become 0. Then it's multiplied by the area scale, so still 0, and finally offset by the character's location. This indeed ensures that the center point on the grid corresponds to the character's X and Y position. And the neighboring UV coordinates in the 2D grid now corresponds to neighboring world positions around the character in that area, if that makes sense. Using this world position, the goal is to fetch the ground height, which we will compare to the rasterized shape's depth. But before we continue, let me rewind for a moment and go over this bit again. In my character blueprint, I access the dual depth manager and call its setAttachment function, passing in the character mesh. This enables the manager to use the mesh location to quote-unquote attach the Niagara component. This in turn lets us use the Niagara system's location to get the character's position and makes the so-called rasterization process relative to it. However, there's a subtle but important detail here. The issue is that for certain algorithms, it can be important to avoid subpixel movement. In our case, if you apply subpixel movement, a shape rasterized at two ever so slightly different locations might end up being rendered ever so slightly differently. This can lead to jittering and at times break algorithms that rely on pixel values that should not be linearly interpolated between neighboring pixels. This is relevant in our case, since pixels store the dual depth and are used to derive the time. So I'm not comfortable allowing subpixel translation to occur, even though I haven't noticed any issues. They could exist, as demonstrated a long time ago in another system of mine. To solve this, I snap the Niagara component onto a grid where the grid size corresponds to the area size divided by the number of pixels in the render target. Essentially, if you have a 256 squared render target representing an area in world space of 2000 centimeters, you can calculate the world space size of a single texel. And by snapping the location to these world space texels, rasterization remains consistent. It's like teleporting the pixels exactly as they are, if that makes sense. Alright, that's it for this brief detour. Now let's get back to finding the ground height. If the world is flat at z equals 0, the ground height value could simply be 0. Except that we are looking to render the depth, quote-unquote, below the ground. In other words, we are interested in shapes that intersect with it. So we assume an arbitrary ground z offset. and a good starting value might be the average foliage height in centimeters that you'll interact with most often. Say maybe half the character's height for tall grass or something like that. Now, of course, the world is rarely flat at z equals 0, so things can get complicated, and there are many ways to get the ground z. It really depends on how your world is built and your preferred method. If you're using a landscape, you could simply sample the landscape height using Niagara's landscape interface. You could also use a scene capture component to render the world z from above in a texture, or use runtime virtual texture to handle it for you. Another option is to rely on the global mesh distance field to approximate the ground z. That's what I do here using an iterative approach. Starting with the x and y world position constructed from the UVs earlier, and an arbitrary z position, typically the character z, I sample the global mesh distance field a first time to get the distance to the closest surface. Then I move down by that distance and repeat the process a couple of times. This usually converges towards the correct ground z, though it's not always perfect. The issue is that we're looking to find the ground z, so our initial z position for the search has to be arbitrary. And while using the character z is a decent starting point, near the character at least, it may not hold true farther away, and the iterative algorithm may fail in some cases. So it's not perfect and comes with all the quirks of using the global mesh distance field, but it can get the job done, is relatively cheap, and comes with no extra memory cost. But you do you. To summarize, here I output the ground z fetched by whatever method you choose, offset by an arbitrary amount. By default, I've set this offset to 90 centimeters, which is half the character's height. Again, since this is a user parameter, it's tweakable via the manager blueprint somewhere around here. For every cell in the grid, I now know the ground z value at which any shape should trigger foliage interaction. And that's where the troubles really begin. Let's ignore this bit for now and focus on the HLSL code. Here's a struct containing the ray tracing functions for spheres, boxes, and capsules. And here's another struct with a function to rotate a vector using a quaternion. Using structs is a workaround that allows you to call functions within custom HLSL nodes. I create a variable of that struct type so I can later call the necessary functions, nothing fancy. Anyway, I'm looking to rasterize the shapes from below, meaning I want to find the overall minimum z so I can compare it with the ground z I computed earlier. I initialize the minimum z to a very high value so that the first min operation will always output the first actual z value, whatever it may be. Next, I get the number of shapes in the data channel. Then, from the small integer array from earlier, I retrieve the necessary indices to compute where capsules, spheres, and boxes start and end in the linear buffer contained in the data channel. Here I initialize the ray tracing. The ray's origin is the world position computed from the UVs earlier, with the z component corresponding to the character's feet. However, shapes may be further down, like downhill or something. So the ray's z origin is instead set to be the ground z shifted by some arbitrary negative amount. That way, with an upward ray direction, I can rasterize the shape's depth from below. So next, I iterate through all the shapes. First, capsules. I fetch the shape data from the data channel, and this might already be puzzling. Where the heck is this function coming from? I've explained this in a previous video, but I'll go over it again briefly. So you can read data from a data channel reader, but the read node is kinda dynamic, right? You have to specify the actual struct you expect the data channel to contain, and the node will adjust accordingly. And when you want to iterate through all the elements, you need to do that within a for loop. And sure, you could use a map for and stick to using nodes. But when things start to get complicated, nodes can be cumbersome to work with. I prefer sticking to HLSL, especially because, unlike material graphs, where constant folding is a thing and you want to use nodes as much as possible, there are no downsides to using custom HLSL nodes in a GPU Niagara emitter. But that means getting the read function for that Niagara data channel reader interface in HLSL is a bit tricky. Basically, you have to trick Niagara into thinking you're reading the Niagara data channel using nodes. That way, it generates all the boilerplate code for that interface. Once that's done, you can access the functions it generated for reading the proper structured data from the data channel. And you can sort of guess what the function will be named. For me, my interface is called NDC reader, stored at the emitter level, so the function will always be named as follows. The function name, followed by the emitter namespace, the interface name, the first variable to read from the struct, its variable type, the second variable, its type, and so on. And the arguments are the index of the element to read, a boolean for success, and the necessary variables to output the struct variables. And if you're unsure, you can read a single entry using nodes and then inspect the generated HLSL code. In there, you'll find the function to use. Back to the code. I perform a safety check to avoid ray tracing invalid capsules. And then I check if the capsule is aligned enough with our ray direction. If it is, I ray trace against the top or bottom sphere instead, as it's cheaper and more robust. For some reason, this capsule trace code fails when the capsule is perfectly aligned along the z-axis. Not sure why. But if it's not aligned, I proceed with ray tracing the capsule as usual. If the ray hits, I compute the hit position by adding the ray origin to the ray direction multiplied by the time of the hit. I only care about the z value though, which is then fed into a min operator to always store the minimum z. Multiple capsules might overlap at the same position, but I want the overall minimum z value, right? Then I repeat the process for spheres and boxes, which gives me the overall minimum z value, if any. Finally, I compare that value with the provided ground z to determine the intersection depth. This gives me the intersection depth that you can see here. Now, shapes are rasterized relative to my character, and as I explained earlier, this is going to be an issue. So in the second simulation stage, still iterating on the same 2D grid, I override the depth value for any grid cell with the depth value from another grid cell. The reasoning here is that I've rasterized the shapes with a certain location as the origin. And now I want to undo that location shift and undo the centering on the character. The goal is to create a 2D grid where its quote-unquote corner is now back at the world origin. This gives me the rasterized depth in world space. It's a bit of a bizarre concept to grasp. Anyway, now that we have the intersection depth, it's just a matter of computing the dual depth, which will be a persistent effect. This means, unlike the depth value that is simply set new each tick, whatever value is stored in that other 2D grid will be iterated on and fed back into the grid. So I need to fetch the value before setting it, which means I need to initialize it first, using a simulation stage that only executes upon simulation resets and iterates on the second 2D grid, the one meant to store the dual depth. I initialize a vector4 value. Why a vector4? Well, I want all my render targets to be double buffered. This means I want to store values for the current frame, but also values for the previous frame. This allows Unreal Engine to derive a velocity when computing world position offsets, which is an absolute necessity for minimizing ghosting due to temporal effects. So since I want to store the dual depth in that 2D grid, so two floats twice, I use a vector4. The first two components store the current frame's dual depth, and the last two components store the previous frame's dual depth. In another simulation stage, which always runs and iterates over that second 2D grid, I update the dual depth. First, I create UVs based on the character's location, just like before. This lets me create a box mask that follows the character around. And I think I can just do that to illustrate it. Yeah, see? Next, I fetch the depth from the first 2D grid. Then I fetch the dual depth from the second 2D grid, the one we are iterating on. So I can use the stack context to access it. I then fade the depth in the green channel by subtracting delta time multiplied by the fade rate. Now, this is a bit of a hack, and it's something mentioned in the tech talk. It's meant to address an issue where things are standing still, but moving ever so slightly due to idle animations. Grass animation may pop in and out because the shapes are subtly moving. So the idea is to prevent the depth from fading at all where anything intersects with the ground this frame. It helps, but it's still not perfect, unfortunately. There's room for improvement here for sure. Maybe we could detect when the character is in idle and snap shapes to the averaged bone location during the idle animation or something. Anyway, next, if the new depth to write is greater than the faded depth, we need to overwrite both channels. I also fade them both based on the box mask to prevent distant objects from persisting in the render target. So as you move away from things, the depth history gets erased. Finally, I create the double buffer. I copy the current dual depth to the blue and alpha channels, and then overwrite the red and green channels with the new dual depth. Voila, we're almost done. At this point, we just need to use another simulation stage that iterates over the 2D grid to access and export the double buffered dual depth to a render target. Ta-da! What you're seeing is the character running around and leaving a trail of depth history, both for the current frame and the previous one. And if I say spawn a ragdoll, you can see its depth history as well. If I move far away from it, it disappears and then reappears when I'm near it again. Cool. Now, I've built some debug tools to help visualize what's really going on. They're out of the scope of this video, so I'll just fast forward through this part. Basically, I'm using the character's Y location to determine which slice of the dual depth render target to debug. Then I use a little compute shader to draw a debug view of that slice. It's costly, but I don't care. As I move in X, I can see the dual depth being filled along that slice. And if I move in Y, it scrolls up and down within the dual depth render target. This helps visualize what's going on. Any shape below that line is drawn in the dual depth render target. The red channel represents the held depth, and the green channel is the faded depth, which slowly fades away, as expected. The difference between the two, along with the fade rate, lets you derive the time of the last intersection. Note that the fade rate itself does not affect the speed of whatever animation you're going to play, right? The fade rate just has to be low enough so that whatever foliage animation you're using has enough time to fully play before the faded depth reaches 0, if that makes sense. And since we are using a 32-bit render target, it can be really slow, and we don't have to worry about precision or animation duration. Foliage could jiggle for a long time if desired. So I guess the next step is to use this render target in our foliage shader. Here's a rough template material. There's already quite a lot going on, so let me try to break it down. I'll skip the more boring details like color and the opacity mask and focus on how the world position offset works. First, there are a few material collection parameters worth mentioning. The scale is expressed in centimeters. It's the same 2D vector that gets sent to Niagara for the rasterization pass. This coordinates vector parameter contains the Niagara component's current XY world position, as well as its previous XY world position. Remember, since the component is snapped to the character's position, this effectively contains the character's position for the current and previous frames. Finally, the fade rate is, well, the fade rate used in Niagara to fade the green channel in the dual depth render target. Now this, well, that's specific to my grass mesh. I baked the grass blade XY pivots into the UVs. But you could also use the Vertex absolute world position. Be aware that this can lead to mesh distortion, since vertices may move somewhat independently instead of behaving as a single grass blade. Using baked pivots is recommended to keep the effect unified per blade. The third UV map contains extra information. The red channel stores a random value per grass blade, which allows me to randomly rotate a vector as a fallback direction in cases where derivatives fail to find a suitable direction, as explained earlier in the video. The green channel contains a top-down gradient, which lets me slightly offset the animation time along the height of the grass to create a subtle delay effect. It's optional. Now, in this material function, I sample the dual depth render target. Since it's already quote-unquote cornered at the world origin, I only need to account for the area scale to convert world space coordinates into UVs. I then sample this texture 2 more times, once offset by 1 texel along the U-axis, and once more offset by 1 texel along the V-axis. The difference between these samples gives me the slope of the depth. I then compute the length of this 2D vector to decide whether to normalize it and use it as the offset direction or fall back to a default direction. This next bit isn't something I'm particularly happy with, but I couldn't find a cleaner solution. Essentially, I divide the 2D vector by the maximum expected slope, saturate it and then flip it. This ties back to the idea that the interaction effect should be weaker when the slope is steep, and strongest when the slope is 0. It's a bit counterintuitive, and I'm actually not entirely sure how this is handled in the God of War implementation. Next, to hide the tiling in the distance, I create a box mask around the character's position. This gives me a fixed XYZ offset to apply to the foliage. Finally, I compare the held depth with the faded depth to derive an interaction time based on the fade rate. In the material, that time is then used to create a cheap spring effect, as discussed earlier in the theory section. This spring is multiplied by the interaction offset, and by an arbitrary value to control the strength of the effect. On its own, this produces this result. I then multiply the offset by a top-down gradient to anchor the grass at the roots. At this point, it's still just as simple to the offset, so it looks a bit unnatural. To improve the result, I apply the spherical reprojection trick described in the same God of War tech talk. This introduces some distortion for larger offsets, but for grass and small plants it's usually not very noticeable, and it's extremely cheap and easy to work with. And optionally, the spherical reprojection vector can also be used to reorient the vertex world normal. Voila, dual depth foliage interaction. Kinda cool. No, it could be something I missed in the tech talk, or something I misinterpreted or wrongfully implemented, but I wasn't too satisfied with the result for multiple reasons. The main issue for me was a noticeable sense of latency in the effect. That latency comes from multiple factors. First, there's the need to cancel the fade where new depth is written in order to avoid weird animation pops with idle animations and jittery objects. So by itself, this only allows the effect to occur behind objects, if that makes sense. Second, I chose to use a sine instead of a cosine for the spring. This is simply about offsetting the starting point of the spring. With a cosine, the effect starts at full strength and fades out. With a sine, it starts at 0, ramps up and then fades out. So using a cosine makes the effect feel much more reactive. But it also introduced abrupt popping that I didn't like, since the interaction effect reaches its maximum in just a single frame. That's quite harsh and doesn't work well with motion vectors and temporal effects. Using a sine, on the other hand, makes the effect smoother, but at the cost of some additional delay. In summary, due to both artistic choices and technical constraints, the effect feels delayed. Also, as mentioned before, this technique does not work particularly well for very slow-moving or jittery objects, such as a character in an idle animation, despite the small hack that prevents the depth from fading where new depth is written. This doesn't completely eliminate popping. And while it could be further improved, I feel like most solutions I have in mind would only add even more latency to the effect. So my solution was to augment this system with another layer, one that focuses entirely on the most recent interactions and idle objects. My reasoning was the following. I'm already computing the intersection depth in world space here, right? So why not export that to a render target and sample it in the material to add a secondary layer to the effect? That's exactly what I did. Remember, this stores how much shapes penetrate the quote-unquote interaction layer. So I can just read it directly to push vertices down and flatten objects on the ground. And let me disable the dual depth layer for a moment so you can see what this does. As you can somewhat see, grass instances that are underneath objects get squished. But it's a bit rough and abrupt, right? It feels almost binary. Either the grass is unaffected or it's fully affected. So my first idea was to simply blur this depth. In a nutshell, I sample nearby depth values using a 3x3 kernel and average them, repeating this process a few times. It's the most basic blur you can get. And that works to some extent, but it still feels a bit rigid. So I thought, why not add a bit of delay? Just enough to give the effect something to work with until the dual depth layer fully takes over. That's what's happening here. I'm creating a persistent effect that involves a feedback loop. So first I need to initialize a value in a new 2D grid. This is a 2D vector used to create a double buffer. In a second simulation stage, I fetch the world depth from the other 2D grid. I add this value to what's already stored in the red channel of the new 2D grid double buffer, but it fades out over time. Then I copy the current value to the green channel before overwriting it, which, well, creates the double buffer. Finally, I fetch the double buffer and export it to a render target. As you can see, the depth leaves some kind of trail behind it, right? And I think it looks much better now. And now, with both layers enabled, I feel like the overall effect is much more convincing. But I'll let you be the judge of that. Feel free to let me know in the comments below. Alright, let's talk a bit about performance. As I mentioned earlier, this is a sort of proof of concept, right? Because a key function is missing from that Niagara interface, I had to rebuild most of it from scratch in blueprints. And the manager blueprint does a lot of work on tick, far too much for me to confidently call this shippable out of the box. Well, it is shippable, but only if you know what you're doing and have a decent game thread budget to afford for this. Speaking of, let's start with the game thread cost. So each ragdoll comes with additional shapes that are iterated over every tick in Blueprint to build the buffer sent to the GPU. And again, since this is all done in blueprints, the cost quickly gets out of hand. That said, this isn't really a deal breaker. Most of the cost comes from the virtual machine overhead. The algorithm itself isn't doing anything particularly expensive per se, although fetching bone transforms can be a bit costly. So a C++ implementation would perform orders of magnitude better than the blueprint version. You could also look into multi-threading, especially since this is purely a visual effect and not gameplay critical, so you could probably even time slice the algorithm and work with a 1 frame of delay or something. So CPU cost, as it stands, not great, but highly improvable by orders of magnitude. Now, what about GPU cost? There are two sides to it. First, the cost of rasterizing the shapes and running the compute shaders. Second, the vertex shader cost in the foliage material due to all this logic. Here again, there's room for improvement. Niagara isn't strictly necessary here, and a C++ implementation would benefit greatly from dispatching compute shaders directly in code, eliminating a lot of Niagara's overhead. The compute code itself could also likely be optimized further. The most expensive compute pass is, unsurprisingly, the one that iterates over all the shapes. Its cost scales more or less linearly with the number of shapes being processed. Now, as I explained earlier, this is a brute force approach, which means you could probably introduce some form of acceleration structure to speed this up significantly. It's not something I know how to implement right now, but I suspect there's potential in first computing a bounding box per shape, to then only iterate over the pixels that actually matter for ray tracing the shapes. Overall, as it stands, the GPU cost isn't too bad. Now, regarding the vertex shader. Well, that's where things get complicated. Before UE5, I would have said this is relatively cheap. Sure, there are 3 texture samples here, but sampling neighboring texels usually isn't as bad as it sounds. Then there's 1 additional texture sample here, and all of that is effectively done twice because we also need to output velocities. Still, with LODs to disable the effect at a distance and some basic optimizations, this isn't particularly concerning, to me at least, unless you're dealing with foliage that has an enormous vertex count. After UE5, with Nanite, virtual shadow maps and all that, yeah, it feels like we've gone 10 years backward in terms of vertex shader cost. As far as I know, Nanite evaluates world position offset 6 times, and any vertex animation leads to virtual shadow map invalidation, which is super costly and so on. It's not great. I personally tend to stay away from Nanite, Lumen and related features, so I'm in all honesty not knowledgeable enough to give solid advice here. You'll have to experiment and see how it behaves in your own project. Remember, this was shipped in a Game of the Year title, so there's no denying that the solution is both viable and performant. The devil is in the details though, and matching the level of performance achieved by Santa Monica Studio on God of War will ultimately depend on your own implementation. And with my own implementation, I'm definitely far from best practices, blueprints and all that, and only scratching the surface. That's it for today's video. I hope you learned something along the way. As usual, a huge thanks to my patrons for the ongoing support, and thanks to you for watching as well. If you liked the video, consider leaving a like and subscribing to the channel. I'll see you in the next one. In the meantime, take care of yourself. Bye bye!